How do chemical reactions occur? Well, we know that at the electronic level they occur because electrons can lower their energy by getting access to lower energy states in a molecule than they occupied in the atoms of which that molecule was made. There's much more to it, though, than that. If we consider reactants in solution, they have to come together by a process of random diffusion. So this is one rate-limiting step in a reaction, and we will talk about this later on. But even once they are together, both atoms are locally in a minimum energy configuration, and to form the molecule, they have to undergo some distortion. This requires thermal fluctuations to drive them into a state in which the two atoms are halfway between being two atoms and a molecule, and it's exactly the reason why chemical reactions require an energy input. You should be glad of this, or gunpowder would always be spontaneously exploding. Let's look at this in a little more detail. This slide shows schematically a diagram of the free energy, and I use the word free energy because, of course, the entropy of the reactants and products are changing because their relative numbers change, and so this needs to be a free energy plot versus something called a reaction coordinate. Now, a reaction coordinate would be very easy to understand for something very simple, like two hydrogen atoms coming together to form a hydrogen molecule. It would simply be this distance between the atoms. In the case of something complicated like the reaction of a nitrogen molecule with three hydrogens here to form two ammonia molecules, it's a much more complex coordinate. So the coordinate, the horizontal coordinate here, is some very complex addition of the coordinates of the individual atoms in the molecules that is derived to somehow measure the progress from a set of isolated molecules here to two ammonia molecules here. So this is the reaction coordinate. Bear in mind it may be very hard to define. Now at this point here, the reactants, the hydrogen and the nitrogen, are in a local energy minimum. Of course, they fluctuate around because of thermal energy, but this is their minimum energy right here. The same is true of the products, only the minimum energy of the products is lower because they are the molecules. However, preventing reactants from going to products is the fact that they need to reach this state here. Specifically, they need to reach it because in order for electron transfer to occur through Fermi's golden rule, we require that the energy of the reactants and the products be the same. So at this point, there exists some distorted form of the ammonia molecule, which I've done rather a bad job of trying to draw. That is neither a nitrogen molecule and three hydrogen molecules, nor two ammonia molecules, but a high energy excited state of the hydrogen and nitrogen that once it reaches this transition point can either decay back again or decay down in this direction to a yet lower energy state, which is the ammonia molecules. The existence of a transition state was discussed by Henry Eyring, who formulated transition state theory. And so Eyring pointed out that there must be such a barrier for a reaction to occur, which he called delta G plus. So the Boltzmann factor for the rate of crossing this barrier is given by e to the minus delta G plus over kT, or RT if it's a mole. Then the question is, what is the actual rate of crossing? To calculate this, one needs to know the attempt frequency, and Eyring argued as follows. He said, well, supposing the system is vibrating at a frequency mu, and that frequency is driven primarily by thermal fluctuations, then Planck's constant times mu is an energy. Let's set that equal to kT, and the result is then that this prefactor in Eyring theory is kT divided by Planck's constant. This approach is put on a firmer footing by a theory of Kramers, who examined the noise-driven escape of a particle from a multi-valued potential. So what I'm showing you here is actually a simulation for a quartic potential, so each of the minima are the same here, with positions at -1 and 1 on this figure. And the panel on the right shows the occupancy of the particle, either in state +1 or state -1, as a function of time. Now you notice straight away that the particle spends very little time making these transitions. The reason for that is this transition state energy here, which I'll call E sub B, means that the probability of being here, or indeed anywhere but the minimum, is much less than the probability of being on the minimum on either side. And therefore, the system appears to make rather abrupt transitions between the two states. It behaves as what is called a two-level system, even although the potential surface is much more complicated, but it's the Boltzmann factor that results in this behavior. So Kramers went ahead and solved the problem of the rate at which a particle stuck in a potential well like this, with a barrier to reaching a second potential well, would cross from here into the second well. In order to model the potential surfaces rather more accurately than Eyring did, he fitted to both these minima and this saddle point here harmonic models. Now what do I mean by harmonic models of potentials? Well, for a spring, so a mass on a spring which is a harmonic oscillator, the energy is given by 1/2 times the spring constant times x squared. That is a parabola. Given that the angular frequency of a harmonic oscillator is given by the spring constant divided by the mass, and notice that the spring constant as it appears in front of this expression is just the second derivative of this potential, we can write down for the curvature of these potentials then that m omega squared is d2e dx squared. So Kramers characterized these wells that way, and so the curvature here is omega A, the curvature here is omega B. These are the two curvatures that matter for this transition, and this energy barrier then he called EB+, and the result was that the rate of transitions in this direction is given by K plus is omega A, omega B, over 2 pi gamma, where gamma is a friction coefficient, e to the minus EB over KT. We will use a slightly different version of this result when we discuss force spectroscopy measurements. Another way to characterize this potential, completely analogous to what Kramers did, is to look at the distance 1 kT above the bottom of the well and ask what the width of the potential is at this point, or 1 kT below this saddle point, and ask what the width of the potential is at this point. It's equivalent to specifying the curvature, and so calling this LC and this LTS for transition state. The result is that the off rate, or the rate at which a particle escapes from this well, is given by the diffusion constant divided by the product of these two lengths times e to the minus e on kt. You'll recognize, remember, that we had the result that x squared is dt, so this prefactor is 1 on t as it should be.